we are going to analyze the scattering of identical particles in this lecture. Now, as you know, for two identical particles confined to a one-dimensional box, the normalized two-particle wave function is usually represented by psi of x1 comma x2. Let's consider a one-dimensional box. Assume that it's a one-dimensional box and you have two particles, two identical particles within this one. So what this two-particle wave function tells you is that you have two particles. Let's say one is at position x1 and other one is at position x2. Then if you take the modulus square of these things, psi of x1 comma x2 dx modulus square, then dx1 dx2, and then this will tell you the probability of finding simultaneously one particle for within an infinitesimal distance dx1 at position x1 and the second particle within an infinitesimal distance dx2 at position x2. Since we don't know which of the two indistinguishable particles we are finding where, then psi of x1 comma x2, the modulus square of psi of x1 comma x2 must be equal to psi of x2 comma x1, the modulus square of psi of x2 comma x1. So what it means is that this one tells you that this is the two particle wave function with your particle 1 at position x1 and particle 2 at position x2. Now on right hand side we again have the two particle wave function, but the position of the particles interchanged. That means the particle 1 at x2 and the particle 2 at x1. So this must be identical, since we are considering the identical particles and there is no way of distinguishing those two identical particles. So this is a condition which has to be satisfied. Now from this we can infer that there are two possible wave function symmetries. Since the squares are equal, you can write psi of x1 comma x2 is equal to psi of x2 comma x1. This is one possibility, because if you square these things you will get the same thing on both sides. Now another possibility is that psi of x1 comma x2 is the negative of psi of x2 comma x1. This will also, when you take the modulus square, will give the same result. So these are the two possibilities for the wave functions, and the particles which satisfy this condition, that is psi of x1 x2 is equal to psi of x2 x1. So that means even if you interchange the position of the particles, there is no change in the sign of the wave function, then such wave functions are called symmetric wave functions. So this is a symmetric wave function. Whereas in the second case, we have seen that when you interchange the position of the particle, the sign of the wave function gets changed. Then such wave functions are called antisymmetric wave functions. This is antisymmetric wave functions. And the particles with symmetric wave functions are usually called bosons. So this is bosons, and the particles with antisymmetric wave functions are called fermions usually. Now let's consider two identical particles that scatters of one another. So we have one particle here and another particle here, and these two are identical in all sense, so that we cannot distinguish these two things. So let's say this is S1 and this is S2, and they are going to scatter one another. Now the momentum conservation demands that if one of the particles, suppose after scattering, let's say our particle S1 is scattered like this. So let's say we have a detector here D1. Now if you compare, let's say theta is the angle which the scattered beams makes with respect to its initial direction, then The momentum conservation tells you that, or it demands that, if this particle or if the particle S1 is scattered through the angle theta, then the other one must be scattered in the direction pi minus theta for the conservation of momentum. So this one will be exactly opposite to this one. So this angle will be pi minus theta. So if you have detector here, let's say D2. So this is the situation of the two particles considering the conservation of momentum and energy. Now in classical mechanics, the differential cross section for the scattering is given by d sigma by d omega. Let's say this is classical. This is d sigma by d omega of the particle which is scattered through the angle theta plus d by d omega of sigma, or d sigma by d omega of the particle which is scattered through the angle pi minus theta. So this is this classical expression for the differential scattering cross section. So this will give us the scattering amplitude f of theta for the particle scattered through the angle theta plus the scattering amplitude f of pi minus theta for the particle scattered through the angle pi minus theta. So this is the classical case. So let's say this is our equation number 4. Classically, actually we could tell which one is scattered through the angle theta and which one is scattered through the angle pi minus theta if you keep track of it. However, in quantum mechanics, there is no way of distinguishing these two particles in their center of mass frame. So that means if you consider the same phenomenon, let's say, let me redraw it. We have two particles, S1, S2, and suppose this one is scattered through an angle theta and this one is scattered through an angle pi minus theta. So this angle is theta and this angle is pi minus theta. Now you consider this situation and let's consider another situation for the same two particles, S1 and S2. So in this case, the particle S2 scatters through the angle theta and S1 scatters through the angle pi minus theta. Now classically, if you use classical mechanics, you can distinguish these two cases as you can clearly track the particles. However, in quantum mechanics, there is no way to distinguish between these two scattering. You won't be able to tell whether S1 is scattered through the angle theta or S2 is scattered through the angle theta. So these two will be the same situation or same condition as far as quantum mechanics is concerned. In this particular scattering example, the overall wave function must be either symmetric or antisymmetric under the interchange of identical particles, depending on whether the particles are bosons or fermions respectively. So if we consider the scattering of identical bosons, let's first consider the case of bosons. Then the wave function is symmetric, the two particle wave function is symmetric, and we can write the scattered wave function as psi for symmetric wave function, psi of r is equal to some normalization constant. Then we have e raised to I k0 dot r plus e raised to minus I k0 dot r plus e raised to I k r by r. Then what we have is f of theta plus f of pi minus theta. So this is the expression for the scattered wave function if you are considering the boson scattering. Now what is this? A is a normalization constant, and this term e raised to I k0 r, now it represents an incident plane wave of the particle which moves in the positive x direction. So let's say this particle, for this particle we have e raised to I k0 r. Now the second term e raised to minus I k0 dot r represents a particle which is moving along the negative x direction, that is along for this particle S2. Now this one, the third term, is basically a spherically outgoing wave, but in this case we have two possibilities, two particles, and those are identical. Then we have f of theta and f of pi minus theta, the scattering amplitude of the spherically outgoing particle. So this is the general expression that we have seen in previous classes, that after scattering, the total wave function will be consisting of the incident wave function and then spherically outgoing wave function. So the first two times are the incident wave functions, and the last two times are, or this term is the spherically outgoing wave, which is one is scattered through the angle theta and the other one is scattered through the angle pi minus theta. Hence, the scattering amplitude of bosons can be written as f of theta, let's say for boson, this is f of theta plus f of pi minus theta. Let's say this is equation 5 and this is equation 6. So once you know the scattering amplitude, the associated differential scattering cross section can be written as d sigma by d omega for boson. So this must be the square of the scattering amplitude. So you can write it as f of theta plus f of pi minus theta, the modulus square of this thing. That means this is the modulus square of f of theta square plus the modulus square of f of pi minus theta. Then we have f star of theta into f of pi minus theta plus f of theta into f star of pi minus theta. Now this last term within this bracket, this term, now this represents an interference term. So this is an interference term, and the star indicates the complex conjugate. In first case, the complex conjugate of f of theta, and in the second case, the complex conjugate of f of pi minus theta. So this differs from the classical equation, because in classical equation what we have seen is up to this. Now in the quantum mechanics case, there is an additional interference term which leads to an enhancement of differential scattering cross section at some particular angles. So let's consider the differential scattering cross section for the angle theta equal to pi by 2. Okay, then we can write the d sigma by d omega for boson at angle theta equal to pi by 2. So this will be, if you take theta equal to pi by 2, your f of theta and f of pi minus theta both will be identical. So you will be having totally 4 terms. So you can write it as 4 times f of pi by 2 square. Okay, because in this case pi minus will be again pi by 2. So these two terms will represent the same angle, pi by 2. So this will give you 4 times f of pi by 2 whole square. Whereas if you do the same thing for the classical expression d sigma classical by d omega for the same angle pi by 2, you can see that this will be 2 times f of pi by 2 square, because in equation of 4 we have seen an expression for the differential scattering cross section which was identical to these first 2 times of boson scattering cross section. So this will give us 2 times f of pi by 2. So you can see that quantum mechanics tells you that the differential scattering cross section at some particular angles are much larger, or twice that of the, or twice of the value predicted by the classical mechanics. And this happens because of this interference term in the differential scattering cross section. Now let's consider the scattering of two identical spin half particles. Let's say two identical spin half particles. So those are basically fermions. Now the overall wave function of two spin half particles can either be symmetric or antisymmetric. So if the two particles are in the spin singlet state, then the spatial wave function is symmetric, and in that case you can write the d sigma by d omega. For the singlet case, this is f of theta plus f of pi minus theta, like what we have seen for the case of bosons in equation 6. So in this case they will be having symmetric wave function, so we have an identical equation as that of the bosons case. On the other hand, if the two particles are in the spin triplet state, then the spatial wave function will be antisymmetric, and in that case the differential scattering cross section can be written as d sigma by d omega in triplet state. So this is equal to f of theta minus f of pi minus theta square, because in this case it is antisymmetric. The wave function is antisymmetric. Here the wave function is symmetric. For singlet state the wave function is symmetric, for triplet state it's antisymmetric, so you have this negative sign instead of this plus. So if incident particles are unpolarized, then the various spin states will be equally likely. So the triplet state will be 3 times as likely as the singlet state. So for unpolarized fermions, you can write a general expression d sigma by d omega for fermion. So there will be 3 by 4 of triplet states possibility. So d sigma by d omega by triplet state plus 1 by 4th of the singlet state, d sigma by d omega singlet state. So you can write it as 3 by 4 f of theta minus f of pi minus theta whole square plus 1 by 4 f of theta plus f of pi minus theta, the modulus square. Now if we consider the case, a particular case, suppose a beam is scattered through an angle pi by 2, then you can see that this d sigma by d omega for singlet state, this will be exactly similar to what we have seen for the boson case. So this is 4 times f of pi by 2 square. Whereas in the case of triplet state, this will be d sigma by d omega triplet state. This will be 0. So these things you can easily infer from these equations. See, for singlet state, for the angle pi by 2, this is f of pi by 2, and this one is also f of pi by 2. So what you have is 2 times f of pi by 2 modulus square. That will give you 4 times f of pi by 2, like this one. Whereas in this case, this is f of pi by 2 minus f of pi by 2. So the scattering amplitude will become 0. So for the triplet case, you can see that this differential scattering cross section will be 0. Now, for the unpolarized case, that means the incident particles are a mix of triplet and singlet state. Then you can see that again for the same angle pi by 2, you can write the d sigma by d omega for fermion. This is 1 by 4 times 4 of f of pi by 2 square, and the second term will be 0. So this is simply f of pi by 2 square. So which is, if we compare the value of d sigma by d omega for the classical expression that we have seen just before, this is half the classical expression value, right? Because in d sigma by d omega in classical expression, what we have seen is, see, d sigma by d omega for classical expression, what you have is 2 times f of pi by 2. So now what we have seen is that for the case of fermions, this is half of the value predicted by the classical mechanics. And you can see that the scattering cross section for fermions are 4 times smaller than the case of bosons, because for the boson case it was 4 times f of 5 by 2, then whole square. Okay, so it is 4 times smaller than the case of bosons.